Lewis structures are one of the simplest representations of atoms that we can actually come up with. Okay? When we're talking about a Lewis structure, we're looking at individual atoms and how many valence electrons they have. All right? And we actually denote these valence electrons by dots. We know that the maximum amount of valence electrons that an element can have is the elements in group 18, also known as your inert or your noble gases. So if I take something like neon, okay, neon, its symbol is Ne. To draw valence electrons, you're simply going to draw dots for the number of valence electrons that element has. No orbits, no protons, no nothing. Just dots to represent the number of valence electrons. So we know that neon has 8 valence electrons. So the way we draw Lewis structures is that we draw 2 dots on top, then we go to the side, then we go underneath, and then we go to the other side. This is the maximum amount of valence electrons that can be on any element. If I give you something like aluminum, okay? Aluminum is in what group? Check your periodic table. So aluminum is in group 13, but when we're looking at valence electrons, it's the Roman numeral 3 with the letter A. So if it's got 3 valence electrons, we will then come up to it and we will start off. The way it works is you sit there and you put 1 on top, you put 1 on the side, 1 on the bottom, 1 on the other side, and you go back to the top. So 5, 6, 7, 8. So if aluminum only has 3, we start at the top with 1, we go to the side for 2, and we go to the bottom for 3. That's how we would draw aluminum. Now, the cool thing about Lewis structures is that you can actually show elements bonding together, different atoms to form molecules. And we are going to revisit this in chapter 2. But if we look at something like sodium, how many valence electrons does sodium have? Sodium has 1 valence electron right there. If we look at chlorine, how many valence electrons does chlorine have? It has 7. So 1, 2, 3, 4, 5, 6, and 7. Okay? When we actually want to show sodium chloride together, we can actually do this forming Lewis structures. Okay? So this is actually the Lewis notation or Lewis structures of the molecule sodium chloride. All right? So when we talk about Lewis structures, we're talking about valence electrons. Okay? And this is the symbol for electrons, E negative, because electrons have a negative charge to them. If I was helium, okay, how would you draw helium? You would draw its symbol, which is He. Now, how many valence electrons does helium have? It does not have 8 valence electrons. Helium only has how many protons to it? Therefore, it only has, helium is the one trick here. Helium will only have 2 valence electrons because helium only has 1 orbit. It is in the first period. And the maximum amount of electrons in the first period is 2. So helium's outermost shell, which is its only shell, is full. But that shell only has 2 electrons. That is the only exception to the rule. Every other element in group 18 has 8 valence electrons. Okay? The second really important representation of atoms that you need to know and understand, and again, we are going to use these a lot, so you're going to get accustomed to, is the Rutherford Bohr model. Okay, now, what was Rutherford's big contribution to the atomic model?
He discovered that there is empty space in
Yeah.
the atom, that it's not stuck together.
And what else did he discover?
The nucleus.
What did he realize was in the nucleus? Positive molecules that we later named protons, right? Those alpha particles that we knew they were positive. Those live in the actual nucleus. So when we represent the Bohr-Rutherford model, we're not actually talking about any neutrons in the nucleus. We haven't learned about that yet. This comes before Chadwick. Okay? What was Bohr's big claim to the atom? What was his big contribution? Niels Bohr did what? So oftentimes when you look up just Rutherford, you'll see that there's a number with a plus sign in the nucleus, and then you might sometimes see this like Jimmy Neutron sort of thing, right? Yeah. Do you see that? Okay, because Rutherford didn't care about the electrons. He did not care where the electrons were. That wasn't part of his experiment. Okay? He did not look at them. He was focused on other stuff. Bohr, on the other hand, said, yo, Rutherford, I like what you did with the nucleus. I dig it. It makes total sense to me. But I don't really think that electrons are just wherever they want to be whenever. I think there's way more structure there, and electrons have set spaces. So Bohr adds on to Rutherford's model. We basically will draw out a Bohr-Rutherford or Rutherford-Bohr model by giving the atomic number in the nucleus. So let's say I wanted to draw, let's say I wanted to draw fluorine. Okay, what is fluorine's atomic number? Period 2, group 17. Its atomic number is 9. So I'm going to put a 9 plus in the nucleus. I'm not putting F, the symbol. The symbol does not go on this style of model. You simply put the number of protons in the nucleus. So that is Rutherford's contribution to this. Bohr's contribution to this is the orbits. What period is fluorine in? Period. Row. Period is a row. Which one? 2. Therefore, fluorine will have 2 orbits. What is the maximum number of electrons that can go on the first orbit? 2. So I like to draw them in little X's, so I will just draw 2. How many do I have to draw in the second orbit? 2 plus 8? No. How many? I need a total of 9 little X's. How many am I missing? I've got 2. I'm missing 7. 1, 2, 3, 4, 5, 6, 7. Okay, this is a representation of a Rutherford-Bohr atomic model. The model not only has to have the atomic number, which is the number of protons, But it also has to have orbits with the correct number of electrons on each orbit. We know that the first orbit is going to have how many? A max of 2. The second orbit has a max of 8. The third orbit has a max of 8. The fourth orbit has 18. The fifth orbit also has 18. And then we move out to 32. And another 32.
Are you sure it's 16? Yeah.
16 or 18? Oh, 16. Whoops. My bad. I wrote 81, so there you go. That's a little bit wrong. Okay, so 16. 16. So the question here that I really need to take home is that whatever your atomic number, whatever your number of protons, you must have that same number of electrons. Because in nature, all atoms are neutral. And if you've got a certain number of positive charges, you need to have the same number of negative charges to cancel out those charges. Okay? Later on, we're going to get into something called ions, which is where they're not equal. And we're going to talk about why that is. But for now, if I've got 9 plus in the middle, then I have to have 9 little minuses floating around somewhere. Because overall, that whole atom has to have the same number of positives as it does negatives. Because an atom in nature is neutral. If you've got -2 and you want it to be neutral, what do you have to add to it? +2, and they cancel out, right? The same thing applies for atoms. Okay? So the question was, how is it that we know that in the first actual period, or the first orbit, you can only have 2 electrons. In the second one, you can have 8. Third one, 8. Fourth, 18. 18, 32, and 32. And the reason is, if ever you're unsure about what the maximum number of electrons in each actual orbit is, look at your periodic table and count how many elements are in each row, each period. So in the first period, we've got 1, 2 elements, maximum number 2 electrons. In the second one, we've got 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. In the third, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. If you count here, you will get 18. Here, you will get 18. If you count these guys, all of these guys, and all of these guys, you will get 32. That is how we know how many electrons go on each orbit. The question is, what would happen if you had something like 12? So let's take 12 here. What do we know has atomic number of 12? Which one is it?
Magnesium.
Magnesium. So, magnesium is in what period? It is in the third period. Therefore, it will have how many orbits? 1, 2, 3. What is the maximum number of electrons that can go in that first little period? 2. 1, 2. What is the maximum number of electrons that can go in the second period? 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, let's do a running total. How many was in the first period?
2.
How many in the second period?
8.
For a total of?
10.
How many are we missing?
2.
1, 2. How many valence electrons should magnesium have?
2.
Holy guacamole, 2.